Hello, I'm Alexander Miramontes, and today I will be presenting my Physics 2212 Lab 2 report. To start, the purpose of Lab 2 is to build from the concepts of Lab 1, such as electric force and electric charges, to get a closer, accurate number for the charge and electric force for the tape by using the line charge method. Before moving on to the computational models code, I'll need to talk about the concepts used in Lab 2. The first is Coulomb's law, then superposition, in which several point charges are used to model the electric field, then divide the object into several segments and sum the electric fields of each segment, and finally Newton's second and third laws. In this first part of the model's code, we have the constants in which some of them are values used from Lab 1, such as the mass of the tape, the length of the tape, and the distance between the tapes. The Q value is the value estimated to get the electrical and the gravitational force as close to equal as possible while using 30 segments. Then we have the function used for calculating the electric field. In this part of the code, we have the function that was given to us as part of the starter code that calculates the magnitude of the electric field from the line charge function as shown here. In this last part of the code, we have a loop that acts as a way to demonstrate the concept of superpositioning. The loop goes through each segment in which there are 30 U's and adds the electric field of each one to get the total electric field of the tape. The arrows are then made to show the electric and gravitational forces. Then finally, the code will print out the magnitude of the electric force and the gravitational force of the tape. When the code is ran, the following computational model is then produced. Keep in mind that when using the value of the charge of the tape found in Lab 1, the arrows will not look equal, and most likely the top arrow, which is the electric force arrow, will be smaller than the bottom arrow, which is the gravitational force arrow. This shows that the value from Lab 1 is not accurate. The amount of segments is also important, since the greater the amount of segments used in the calculation, the more accurate the value will be. Here I use only 30 segments. The Q value that was used in the code and demonstrated with a computational model was found out by adjusting the Q value to where the arrows and the magnitudes of the electric force and gravitational force were close to equal with each other. The Q value that got me close was 2.924 times 10 to the negative 8 coulombs. When using this model, the assumptions made were as followed. We could ignore air resistance in the model. We can assume that the tape is divided into several segments with evenly distributed charge, and every segment has the same charge. We also assumed that the segments can be considered as point charges. And finally, we assume that adding each charge is equal to the net charge on the tape. To conclude this lab report, a question is asked that what if you had modeled each of your tapes as a single point charge? Compare the estimated value of the charge you get when you use your experimental data for the point charge model to the value for the line charge model. The point charge model from Lab 1 gave me a value of 4.04351 times 10 to the negative 9 coulombs, while the line charge value was 2.924 times 10 to the negative 8 coulombs. This results in a 13.8% difference, which shows that the line charge value is more accurate. Another question is that why do these estimates differ, and which value is more likely to be closer to the real value? The way we calculated these values are different, in that for the line charge model, we consider the forces in the x and y directions for the tapes, as demonstrated with the loop in the code, while the point charge model only used the y direction of the force. As such, the line charge model is more accurate to real life.